All right, so today we are diving into one of the most famous experiments in physics.
The double-slit experiment?
Right. It's considered so fundamental to quantum mechanics
Right.
that Richard Feynman said you could basically glean the entire field just by understanding this one experiment. We've got all our research lined up here, ready to go.
Okay.
And we're going to unpack the experiment's history, the different variations of it, and all those head-scratching interpretations that it has spawned. So to start with the basics,
Okay.
we fire these individual particles at a barrier that has two slits in it,
Okay.
and then we watch to see where they land on a screen behind that barrier.
Yeah.
Logically, you would expect to see two bands of particle hits, right?
Uh-huh.
Like corresponding to the two slits.
Right. You would think.
But that's not what happens.
That's not what happens at all.
Instead, we get this interference pattern, like the
Yeah.
kind you see when waves are interacting.
Mm-hmm.
So it's as if each particle is somehow going through both slits
Right.
at the same time and interfering with itself.
Yeah. It's super weird.
Okay, so that's already pretty bizarre, right?
Totally. Yeah.
But to understand just how weird it is, we need to go back in time
Okay.
to the early 1800s
Right.
with Thomas Young.
Yeah.
He was the first to demonstrate this with light,
Mm-hmm.
which actually proved that light has this wave nature.
Yeah. So that was a really big deal at the time because
Right.
there was a lot of debate about whether light was made of particles or waves.
Okay.
So Young's experiment kind of settled that.
Hmm.
But then about a century later, in 1909, G.I. Taylor
Yeah.
did something even more incredible.
Okay.
He did the double-slit experiment with such low-intensity light that he was basically emitting single photons
Right.
one at a time.
So like one tiny packet of light at a
Yeah.
time going through.
Exactly.
This is already blowing my mind.
Well, it gets even weirder
Okay.
because even when sent one by one, those individual photons still formed that interference pattern on the screen.
No way.
Yeah. It's like, imagine watching a screen slowly fill with dots,
Okay.
but those dots are forming these bright and dark bands as if they were waves.
It's like each photon knows it's supposed to create this
Right.
wave-like pattern, even though it's acting like a single particle.
Exactly.
It's so strange. And then to make things even wilder,
Yeah.
Claus Jönsson comes along in the 1960s,
Mm.
and he does the experiment using electrons.
Oh, wow.
And guess what?
What?
Same result. Interference pattern.
So it wasn't just light then?
Nope.
It was electrons too.
It's called electrons, too.
These tiny particles with mass
Mhm.
were acting like waves.
So this wasn't just some quirk about light.
Right.
It was something much, much deeper.
Yeah, about the nature of reality itself.
About the nature of reality itself.
Ugh.
Okay, so I'm officially mind-boggled,
Mm-hmm.
but what happens if we try to actually observe which slit each particle goes through?
So before the break, we were talking about actually trying to observe which slit each particle goes through.
Yeah, like we want to know how it's doing that, right?
Exactly. Like, can we catch it in the act of being both a wave and a particle at the same time?
Right. Like what's really going on here?
So that's the famous which-way experiment.
Okay.
And it's where things get even more shocking.
Oh, boy.
Because when you try to add detectors
Okay.
to each slit to see which one the particle is going through,
Uh-huh.
the interference pattern disappears.
But no way.
It's like they're saying, oh, you're watching now. Okay, fine. I'll just act like a normal particle.
So it knows it's being watched.
Well, not exactly no. But the act of observing, the act of measuring is changing the outcome.
So just by trying to look at it, we're messing the whole thing up.
In a way, yes. This is what's called the principle of complementarity in quantum mechanics.
Complementarity. Okay.
Yeah, so you can measure a particle's position, like where it is,
Okay.
which is like saying, hey, you're a particle. Or you can observe the interference pattern, which is like saying, hey, you're a wave.
Okay.
You can't see both at the same time.
So it has to be one or the other.
Exactly.
Wow. That's so bizarre.
Yeah, it's like it's choosing how to behave based on how we're looking at it.
It's really messing with my head. Now, I've also heard of something called Wheeler's delayed choice experiment,
Oh, yeah.
which sounds even crazier.
Well, it takes this whole observation thing and it kind of pushes it even further.
Okay.
So imagine this. The decision of whether to observe which slit the particle goes through
Uh-huh.
is made after the particle has already gone through the slits.
Hold on, so we're making the choice about how to measure it
Yeah,
after it's already done its thing.
exactly.
So how can our choice affect something that's already happened?
That's the crazy part. It's like we're asking the particle, hey, did you go left or right? But we're only asking after you've already made the trip.
So we're messing with time now.
It really challenges our everyday understanding of cause and effect
Oh, yeah.
and time. But quantum mechanics actually allows for this.
Quantum mechanics breaks all the rules, it seems. And what about this quantum eraser experiment I've heard about?
Right, so with the quantum erasure experiment, we take this whole delayed choice idea and add another layer of complexity with entangled particles.
Okay, remind me, what are entangled particles again?
So entangled particles are these pairs of particles
Yeah.
that are connected in this really weird way.
Ah,
If you measure a property of one of them,
okay.
you instantly know the same property of the other one, even if they're miles apart.
So, like, they're linked.
Yeah, it's like they're two parts of a single system,
Hmm.
even when they're separated by a large distance.
So how does that fit in with the double-slit experiment?
Well, in the quantum eraser experiment,
Yeah.
we send these two entangled particles through the slits.
Okay.
But we do something really tricky with the information about which slit one of the particles went through.
So we're messing with the information now.
We're manipulating it
Oh.
by erasing this information.
Erasing information, what does that even mean?
It's not like we're literally deleting it from the universe.
Right.
It's more like we're scrambling it in a way that makes it impossible to know which slit the particle went through.
So we're making it a secret.
Sort of. And when we do that,
Yeah.
the interference pattern for the other entangled particle comes back, even though that particle had already hit the screen.
Hold on, we're bringing back the interference pattern after the particle has already done its thing.
Yep. By erasing information about its entangled partner. It's like we're changing the past by manipulating information in the present.
This is seriously messing with my head.
It's pretty mind-blowing, right? It suggests that information itself might play a much more active role in shaping reality than we ever thought.
Okay, so we've got particles acting like waves, observations, changing outcomes, and now information that can seemingly rewrite the past.
Yeah, the double-slit experiment really throws a wrench into our classical understanding of how the world works.
It's like the universe is playing by a whole different set of rules.
Yeah.
But before we get too lost in all the quantum weirdness,
Right.
let's take a step back and try to make sense of it all.
Okay.
So we've got this double-slit experiment with all its crazy variations.
Yep.
What does it tell us about the nature of reality itself? So we spent the last two parts diving deep into this crazy double-slit experiment.
Yeah, we've covered a lot of ground.
You've got particles acting like waves, measurements, changing things.
Entangled.
Entanglement.
Entangled. That's-
Information seemingly rewriting the past. It's a lot to take in.
Definitely. It challenges everything we thought we knew about how the world works.
Right. So after all this, what does it all mean? Does it tell us anything about, the nature of reality itself?
I think that's the ultimate question, right? The double-slit experiment really suggests that reality is not as straightforward and objective as we might think. It's not just a bunch of objects with definite properties, all existing independently of us. It points to something much more fluid, more interconnected, and maybe even influenced by our observation of it.
So are you saying that our consciousness is somehow shaping reality? That's a pretty wild idea.
It is a radical idea, and there's no scientific consensus on it.
Okay.
Some interpretations of quantum mechanics, like the von Neumann-Wigner interpretation, really lean into that idea, suggesting that consciousness plays a fundamental role in collapsing the wave function and determining the outcome. But other interpretations, like the many worlds interpretation, they say that consciousness is just kind of along for the ride, experiencing different branches of reality without directly influencing them.
Right, so there's no definitive answer yet.
Not yet, no.
On whether consciousness is actually affecting reality or not.
Yeah, it's still a big mystery.
But it does seem like the double-slit experiment forces us to think about the relationship between our minds and, matter.
Absolutely. It challenges that old idea that mind and matter are separate things, suggesting a more, holistic view where everything's interconnected.
Yeah, like the universe is a participant
Mm-hmm.
in our experience of it, not just a backdrop.
Right. It's a very different way of thinking about things.
So we've got these different interpretations, but is there any way to actually test them?
That's the million-dollar question. Scientists are constantly working on new experiments and technologies to really dig deeper into quantum mechanics and see which interpretations, hold up the best.
So they're still trying to figure it all out.
Oh, yeah. There's still so much we don't know.
So even though this double-slit experiment has been around for over 200 years, it's still a source of new discoveries.
Absolutely. It's a real testament to the power of this seemingly simple experiment. It's inspired generations of scientists, and it continues to push the boundaries of human knowledge.
And with all the advancements we're seeing these days in things like quantum computing,
Right.
I bet we're going to see even more mind-blowing discoveries coming out of this.
Yeah. The future of quantum mechanics is incredibly exciting.
Well, on that note, I think it's time to wrap up our deep dive into the double-slit experiment. It's been a wild ride. But if there's one thing I want our listeners to take away from all of this, it's this. If something as simple as a particle going through two slits can reveal such profound mysteries about the universe,
Right.
then who knows what other wonders are out there waiting to be discovered.
I love that. The universe is full of surprises.
It definitely is, and that's what makes exploring it so fascinating. So to all our listeners out there, keep questioning, keep wondering, and most importantly, keep exploring.